Many natural phenomena follow the exponential growth decay model given by A of t equals A naught or A sub 0 e to the kt, where A sub 0 is the initial amount that you start with. This could be a bacteria population, this could be an amount of metal that is radioactively decaying, could be all sorts of stuff. E is the irrational number, E. T is time in a given unit, often seconds, hours, days, months, years. And K is our growth constant. K will be positive when we talk about a growth problem, for instance, a population growing. K will be negative when we talk about a decay problem, like a radioactive substance decaying over time. So if we are given the problem that a bacteria culture grows at a rate modeled by A of t equals 100 e to the 0.055 t, where t is measured in hours, and we're going to measure our population in grams, then if we want to know the initial amount, well, this occurs when t is equal to 0. So the amount at time 0 is equal to 100 e to the 0.055 times 0, which just becomes 100 e to the 0, or 100 times 1, or 100. So you can see that the value in front of the exponential actually ends up being our initial amount. So our answer would be 100 grams, since we are counting the bacteria population in terms of grams that we can weigh it in. We start off with 100. Our growth constant K can be interpreted in terms of a percent, that is our growth rate. When K is equal to 0.055, can be interpreted as a percent of 5.5%. If we want to know the bacteria population after 7 hours, then we can figure out the amount after 7 hours, which would be 100 e to the 0.055 times 7, which would become 100 e to the 0.385. And at this point we use an approximation to say that's about 146.96 grams. We get our final value by sticking this in a calculator. A question that takes a little bit more work to solve would be, when will the amount reach 175 grams? In this case, we're being given the amount of 175 and being asked for the time, when is it that that will occur? In this case, our variable occurs in the exponent, so it's going to take a little bit more work to solve for. So what we do is try to isolate this exponential piece. So we're going to divide both sides by 100, giving us 1.75 equals e to the 0.055 t. Now, if we want to get this variable out of the exponent, we're going to have to take the natural log of both sides. So on the left, we get the natural log of 1.75 equals the natural log of e to the 0.055 t. And we keep in mind that natural log and exponential base e are inverses of each other. So on the right, we just get 0.055 t. And now to solve for t, we just divide by whatever's multiplying it. So natural log of 1.75 divided by 0.055 is equal to t. Now this is our exact value, but a lot of times we have no idea what that is even close to being. So we put it in a calculator and we approximate it as being roughly 10.17 hours. So you can see I've gone back and I've eliminated some of the work that we did in the previous problem. A moment ago we were asking how long it takes to reach 175 grams of bacteria. We're now asking how long does it take for the bacteria culture to double. So if we started off with 100 grams, we now have 200 grams when we double. When we divide both sides by 100, we're going to get 2. And then what was the natural log of 1.75 through the rest of our problem will now become the natural log of 2. So you can see a lot of the steps you take, a lot of the algebra steps you take are going to be exactly the same in these problems. The only thing that's going to vary is the values that you put in here. But the actual work will look almost identical up to the point where we get to natural log of 2 over 0.055 is equal to t. And again, we like to approximate that so we have some idea of what that means. We get to approximately 12.60.